a pleasure to have Robyn, who's associate professor at UPenn. Robyn did her PhD at MIT, and actually that makes you my academic great aunt. Oh, boy. With Persian girl.
Oh, right. You did your.
He's my great grandfather.
Wow.
Great grandfather. Anyway, academically. Then she had a postdoc.
It's even more
No, I
complicated.
think it's like second cousin once removed.
Oh, really?
Yeah. Anyway,
Wait, who was your PhD advisor?
Hirata, and then Seljac, and then.
Gotcha. Okay.
So, sorry about that. Then it's a fellowship in Colombia and NYU. So I guess this was what, in 2013 or something? No, first at the Netherlands, and then it's a fellowship, then went to Caltech, and then was back here, also joined ECCA. She had the Sloan Fellowship in 2023, and she's been working on going end-to-end from dark matter particle models to what happens in galaxies. Give us a wide angle view.
Thank you.
Go ahead.
All right. Thanks for having me, all. So today I'm going to talk about a subject that I probably don't need to tell you about. So dark matter is 30% of the total energy density in the universe and 90% of all the matter that exerts gravity on everything else. And of course, we don't know what it is. So there are a lot of lines of astrophysical evidence that point to something else being out there that makes gravity but doesn't interact with anything else. And on the other side of the coin, in particle theory, there are some holes about what we can predict for the known properties or the measured properties of even all the known particles. And so for a long time, the game was, can we solve both these problems by just positing some new particles that do that, right? So this is a drastically oversimplified view, obviously. But in order to situate this talk, I just wanted to sort of draw some comparisons between what a particle physicist thinks about when they think about dark matter and what an astrophysicist thinks about, right? So if you're a particle physics person, then you're interested in all these microphysical interactions and different kinds of particles, the properties that they have that descend from the theory that you posit. And there's a whole forest of these theories, right? And as we rule out some of them, people invent new ones. Whereas an astrophysicist is we're really working with an effective description that only has a few parameters because you're looking at much larger scales than the ones on which most of the microphysics is happening. And so you basically just want the cross-section and the density. And then sometimes now people put in things like decay probability or screening scales or whatever, but this is a relatively new innovation among astrophysicists that make predictions for dark matter models. Despite this very large, like zoomed out effective description, many of the strongest constraints we have on dark matter are still astrophysical.
Aren't all of them? Oh, well, I guess.
No, we have constraints from direct detection experiments not seeing anything.
Yes. Yes.
And there are sort of secondary constraints based on what people have and have not seen at the LHC too. So I won't say all of them, but many of them. So I don't need to really explain this to you, but part of the reason for this is that astrophysics has a long time to deal with what kind of dark matter it's got, and for the dark matter to imprint things on the stuff we can see. So here's the Big Bang. Here we are now. Here's a whole bunch of stuff that happens early on. And so if you're looking at like the early universe, and you're basically studying this stuff back here up until the CMB, and that's nice because it's all linear. But if you're studying galaxies, then like the Milky Way, you have information from all of these epochs because the Milky Way has existed for this entire time in some form. You can also constrain properties of dark matter over a wide range of scales from astrophysics. They're all big scales relative to like the Planck length, but you can still differentiate different theories because often those microphysical properties establish things, extra length scales in the problem that are much bigger, right? So this is roughly a scale length versus how much power there is at that scale in the dark matter distribution. If you assume that you have a vanilla model of core dark matter, you have structure at all scales, If you give it a temperature at the beginning of the universe, then it cuts that off at some characteristic scale. And if you give it some kind of self-interaction, you also do funny things to the power spectrum. And so and all of these different scales I've drawn with malice aforethought in the range that we can probe with something like the Milky Way structure. There are other theories, of course, that make predictions that you can probe with other astrophysical sources. So it's a little bit biased for me to say that, but whatever. It's my
Also, we just had a talk a few weeks ago, I'm forgetting the name, who was saying that maybe there's evidence for an increase in the power spectrum
Yeah.
at small
I
scale.
didn't draw that on here,
Right,
but
so
this model
you're being
does that.
fine, good. So I like your cartoon in the previous slide, but you could put it.
I'm gonna draw another line on
Yes,
it,
that
actually.
shows-
Now that
yeah,
you say
Put
that,
some upward feature.
that's a good point.
Below the Milky Way scale.
Right, so ideally we would just, make a map of the dark matter and galaxies and then decide which of these models fits it the best, right? No sweat. Of course, we can't do that because dark matter is not visible. So instead, we have to go and try to infer it by inverting the equations of motion for stuff that we can observe. And so in the Milky Way, the idea was we would, measure the positions and velocities of a skillion stars with this little guy, Gaia. And then, and in fact, Gaia's done this amazingly well. There's billions of stars now for which we can get 5 or 6 dimensions of their phase space information. So not just the positions, but also the velocities of most of the stuff that you see in this image. I should go back for a second because I like to point out that this is not a picture, right? This is not just a camera exposure. This is actually the luminosity from all 1 point something billion stars that Gaia has seen in 3 different color bands added up into pixels. So in principle, you could zoom into this image down to resolving individual stars. That's how awesome Gaia is. All right, so we also get kinematic information from this. So then the strategy is, right, I measure the phase space distribution of the stars, I invert the Poisson-Vlasov equation for some equilibrium population, that gives me the global potential, which then I invert Poisson's equation to get the density, which is going to be the density of the stars plus the density of the dark matter. The approximation is because there's also gas in there. And then I subtract off the baryons, and then I get the dark matter density. Okay, yes.
Is it the second inversion non-unique?
Yeah, so
So how do you constrain it?
there's obviously problems, right? You can already see some of them. Those aren't even the worst problems.
Oh no. Oh no.
All right, so in order to do this, you have to make some assumptions about Milky Way because you need to be able to do those steps 2 and 3 with some sort of prescription for what the dark matter density and potential are. You can measure the density of stars pretty well. So that's not the main problem here. But so a person who does this, their mental model is here's the halo, mostly dark matter. Here's the disk and bulge in the middle. Here's some satellite galaxies going around. There's some things that got tidally destroyed to make streams. There might be, depending on your theory, little clumps of dark matter buzzing around, and there's some nearby galaxies. And then these little star things are globular clusters, but I forgot to put them on my cartoon. Right. So generally people assume that the halo of dark matter is roughly spherically symmetric, it's in dynamical equilibrium, that these satellite galaxies are not significant perturbers to that distribution. The disk and bulge are basically the same for 10 gig years and don't have any effect from the dark matter. That you get these nice simple cold streams from tidal disruption. That the uniform field of dark matter perturbs the streams in some way that you can describe.
But not the disk and bulge.
But not the disk and bulge. Yeah. You know where I'm going with this. So galaxies outside the Milky Way are pretty much undisturbed by its tides. So how's it going? All right, so that's not true. That's also not really a good assumption. This is not a good assumption. This also is not a good assumption. And all these other things probably don't work either. And as you can tell from this biased summary, the stuff that I've been working on is using cosmological simulations of galaxies, which offers some more realism to try to test these assumptions to see whether they work or not, and decide which ones we have to worry about the most. Because I think we can still make powerful constraints on dark matter theories from studying things like the Milky Way. But in order for them to be robust and believable, we need to deal with the mismatch between our assumptions and reality. All right. So the underlying problem here is that the Milky Way is not in equilibrium, right? It's an actively evolving system. And so the question you might be asking is, okay, so why is that? So I'm going to play a movie of a simulation of a Milky Way-like galaxy from the suite that I work with to test these assumptions. And you'll see that there's a lot of stuff going on, right?
Was
movie
that the
spans-
background expansion at the beginning?
Yeah,
So this is in like linear
physical
coordinates.
coordinates. Yeah.
Good.
And you can see that over time, a lot of stuff happens to what eventually emerges by Z of 0 to be the Milky Way, like substance. Right? So there's a lot going on in here, and what it is actually a fundamental prediction of any cold dark matter model that galaxies assemble hierarchically over cosmological time spans. Right? So the fact that our models are not, that our assumptions are not matching what's out there in the Milky Way is actually a confirmation of one of the major predictions of cosmological theory, that galaxies grow hierarchically. All right, so now what do we do though, if we still want to get dark matter constraints? So I'm going to argue there are two things that we need to do. One is have better theory, and the other is to do principled comparisons. All right, so let's talk about this one. This is really the heart of what I want to do. So the first part is that I think we need to use these cosmological simulations that include the evolution of the galaxy within it to make our predictions. And the simplest way to see that is to compare the dark matter distribution you get if you simulate something without the galaxy growing in the middle to the same halo, same initial conditions, but with the galaxy growing over time. And you can visually see differences between these two images. I could put up plots that would show you exactly how big those differences are, but you can see it by eye when you visually compare these two images. And those differences extend from the large scale structure of the halo all the way down to the population of satellites and streams that surround it. And so getting this right is actually very important to making sure that your predictions are realistic enough to match what we see in nature. So this is a lot more expensive than doing dark matter only simulations, because besides the dark matter, you also have to have the hydrodynamics equations in there and then prescribe how your stars form and what happens to their energy when they die. But I think that we have such a lot of powerful data now that it's worth it to do this extra work.
And do you believe that this general approach is converging
Yeah.
on a physical theory for the baryonic sector?
Yes, in some respects. I think you can't globally say that about every possible thing you could compare these kinds of simulations to. But dynamically, I think we've got the basics in hand.
Good.
There are details that I think are also interesting tests of whether we're doing things right. And I can get back to some of those later. But so one thing we can do is to make better models of our galaxy to test these assumptions. And today I'm going to focus on the smallest scales, because that's what's been occupying me most recently. And so the smallest scales, what the constraints we get are often involve both the population of low mass galaxies surrounding a galaxy like the Milky Way, and the ones that got eaten by the galaxy's tides already, and we call those streams. And so this is a still from one of our cosmological simulations, and we're making all the stuff that we see in actual galaxies like the Milky Way. So these are basically the workhorses for the smallest scale constraints that we can get from galaxies. The satellites themselves, the distribution of like the number of them that you get as a function of their mass, it can differentiate between different theories. But more interestingly, below the scale where you have enough mass to make a galaxy in your subhalo, you can look for these with cold tidal streams by looking for where something might have passed through and left a divot in your otherwise cold population. And so this is an idealized simulation, which I'll get back to in a second. But we're seeing like very tantalizing hints about this in real streams. This is a stream that we think is not from a satellite galaxy like the ones we're showing you here, but from a globular cluster. I'll also get back to that. But even satellite streams are constantly bombarded by these little clumps in a CDM-like theory. And so this signal is something that people have been going after, and that's only going to get more so in the near future, because we're about to get data that we can use for this, not just from our own galaxy, but from others nearby. All right. So the basic idea here is that if you have a stream and a subhalo flies by it, it reorders the stars in the stream in terms of their energies, and it jumbles them in a way that either that it produces substructure within the stream. So here's an example that's extreme, where this thing has like a direct hit. But the original idea from this is based on numerical experiments, is that this imprints the mass function of substructures of the dark matter onto these cold kinematic populations. So the larger the subhalo, the bigger the gap, in other words. Right? And we think that we could probably see this not just in our galaxy with resolved stars, but with something like Robyn at up to 5 megaparsecs away. So a key to this model and to the power you could get out of its constraints on dark matter is that we can do this statistically in the near future, not just with the few streams of the Milky Way that we can see that display this kind of substructure. All right.
At that distance, how many Milky Way mass galaxies?
About 50.
50, did you say?
There are 100 within like 10 megaparsecs.
I see.
So less than 50, but still.
But tens.
Tens. Yeah. So that's a big advance over what we could do in the Milky Way. There are a lot of reasons why you can't use every single stream in the Milky Way for this that I don't have time to go into. But backing out that information also implies that you need a model for the thing that made the stream. So typically for the Milky Way, even post Gaia, people model the gravitational potential by superposing a bunch of parameterized models for the different things, and implicitly separating the disk and the bulge and the halo and all this stuff. And this usually amounts to like 15 or 30 total free parameters that you want to model, and that's before you introduce time dependence, which most people don't. All right. And this breaks in several ways if you think about our actual galaxy, but the biggest one is probably the presence of the Magellanic clouds or the Milky clouds. So the tides and the dynamical friction of this merger drags the population of subhalos around in such a way that some parts of the Milky Way will have more than others, and their velocity distribution will be different in some places than others. And if you ignore this and assume that the distribution of these substructures is the same everywhere, isotropic and maybe radially dependent but in density, then you're gonna misinterpret the signal that you might get from a stream. Like these are real streams that we superposed on our model of the LMC interaction. Misread those into an erroneous density of substructures, and therefore it'll weaken your constraints on the dark matter model. So you also have to model the formation of the stream itself. Usually people take one of these time-independent parameterized host galaxies and then if they want to put them in substructures one by hand, aim them at the stream to try to get the thing to make a gap. And the stream itself is made with a prescription where they don't actually simulate the thing it comes from, because most of the streams we use for this are globular cluster streams, and those collisional models are computationally expensive. And so instead, you just decide how you're going to release stars from the Lagrange points, and maybe include the gravity of the progenitor as things sort of leak slowly away. But this results in pretty well organized populations for your stream models, right? You're making a lot of simplifying assumptions here, and so the stream that you get is very long and cold and thin. And so this is a baseline that will almost always overestimate the effect of subhalos, because anything that changes this set of assumptions could create substructure that you would mistake for stuff that came from the subhalos. So you're almost always only going to get an upper limit if you don't use more realistic models for your baseline. Right? So we can use better models, obviously. So the parameterized modeling of the global galaxy is ignoring a lot. Here's a zoom in of what's happening at small scales in one of these things. Boom! Oh my God, this is a redshift of a half, you know? A stream is probably already forming that we might use to do dark matter tests, and yet not until almost the end of this simulation do you actually get something that looks like a static disk and halo. So what we started trying to do is use basis function expansions that solve the Poisson equation to do this instead in a more non-parametric way. And so we started by just trying to fit them to our simulated cosmological galaxies to see like how many orders you need to take the expansion, which kinds of models work the best. And what we found was you could get away with a relatively low order spherical harmonic expansion for the dark matter halo if you used a spline to sort of give you the radial variation in the normalization. And then basically just a Fourier decomposition of the disk as a function of radius. And splitting things up by shape is advantageous if you're going to do something like this, because then you don't have to like ask so much of your spherical harmonics to squish down to make a disk. You can just do this.
Sorry, Robyn, this is absolutely so wonderful, but I'm not grasping about the radial variation via spline fitting. I mean, aren't these spherical harmonics you're using? So how do you change them radially?
Yeah, so you split up the radial basis. In a typical expansion like this, right? You have like the radial basis would be the Lagrange polynomials, and then you have like the spherical harmonics for the angular variation. And so
Right.
what we've done is just put, instead of a set of Lagrange polynomials with a base function, a set of like a thing that fits the base function with a spline. That clear things up?
Oh, I see. You just replace the Lagrange polynomials with a spline.
Yeah.
Or okay, you're not distorting them or something like that. It's not like you add them with a kind of, okay, perfect. Thank you.
Cool. Yeah. It's the same deal with the Fourier series for the disk. All right. So now we can get away from this time-independent parameterization and keep the analytic model part, which is convenient, and guarantee that we're solving the Poisson equation. So you just take this same strategy, you fit all the snapshots of your simulation, you get a whole bunch of these things, and you just interpolate from time to time from the forces that you get from your model. And this turns out to work extremely well, which I'll show you in a minute. But another thing that you can do is control the amount of substructure in your model globally by just choosing a different L max. And so each order in L has a typical angular scale. And so if you pick a certain L to be the maximum order, you're limiting to things that have a certain angular size in substructure. And so for the stuff I'm going to show you, we did this out to L equals 8, which is actually overkill. And if you assume that this is the stuff that can be represented by the model, it's stuff that would be underneath this line. And I took a very conservative value here for how big the thing is, and made it 20 times its scale radius. And so this big blotch up here is all the subhalos in our simulation over 2 gigayears as they move around. And then the red tracks are what the satellites are doing, just because I was curious. And so only the very largest stuff ends up being capable of being represented by the model at all. And so you've essentially made a model of your galaxy that has all the shape complexity, but without the substructure, to get a baseline for what you can do to a stream without invoking substructure. All right. So that leaves us without having to put substructure in one by one, but we can still turn it on and off based on what we do with this model.
Sorry, so L equals 8 for the spherical harmonics, but how many radial?
Oh yeah, the radial spline has knots at like logarithmic separation, so they're more in the middle than there are in the outskirts. At the radius where you expect the subhalos to be, the knots are farther apart than almost all of these things as well, but that's a good point. I was messing around with this slide today, so I can look that up for you afterward, but I don't think
But
that's
not
gonna be the,
parametrically more or fewer.
yeah,
Around the same.
it's around the same scale. I think there's like 20 over the entire virial radius.
By the way, this is one of the first correct uses of the word analytic in our seminar series. It's truly analytic in the sense that you have derivatives to all orders.
Yeah, I'll get
So
back
it's
to that.
analytic.
We're actually exploiting that fact now to do automatic differentiation of orbits in these models.
Yeah,
It's gonna be really
it's
fun.
very exciting.
So here's an example where we reconstruct the formation of a stream. And I've cheated here a little bit because we have the full simulation, so we know when all the stars escape the progenitor. But you can see that you can do a really good job making streams that look just like the ones from the real N body extremely cheaply. All right. So the advantage that we've been exploiting lately is to use these to study streams that we can't resolve in the parent simulations. And by that, I mean globular clusters. So I have a collaboration with a few experts that I think this was really the key, is getting the right people on this project. So since we have a cosmological simulation at the beginning, we can't resolve the globular clusters specifically, but we can tell where in the simulation they would have formed, because you look for places where the star formation is going gangbusters at some like extremely high density, and you're like, okay, well, if I had a resolution, there'd be globular clusters there, right? And then you tag those locations and you can see where they go as the simulation evolves. All right, so Mike Grudish did this in 2023. And then you can hook up a real globular cluster model. So it's not full N-body, but it Monte Carlos over the orbital interactions. So Rodriguez wrote this code called CMC that does this. And so now we can build in actual internal dynamics of the globular cluster while applying the tidal forces that we would predict the thing would experience in the cosmological simulation. All right, so already we're doing better than most people do to try to model streams. And we've gotten rid of the last of these things, except that we still include the gravity field of progenitor for the escaped stars. So now we don't have to prescribe when the stars are going to escape anymore, because the globular cluster model tells us when they leave the tidal radius. All right. And so then we take our BFE of the same system and we trace where the stream stars go once they leave the cluster, using this code that we've already validated to make a good stream out of it. And then eventually we can make predictions for what a survey like Robyn would see for these streams. And so we use this to create the first really cosmologically consistent models of globular clusters. Somebody was on Zoom.
Somebody's zooming.
This is it. Your.
Sorry, I forgot to turn mine off and there's some noise in the background. But since I interrupted you, I didn't assimilate, what was the BSE abbreviation? What does it stand for?
BFE. Yeah, basis function expansion.
Oh, okay, thanks.
Yeah. So these are our first two examples that we kind of cherry picked to look like actual streams a little bit, in the sense that their orbits range over the radii where we see streams in the Milky Way from globular clusters, right? We did not cherry pick them to look like particular streams, but they look pretty convincing, right? This one, as it evolves, gets like pretty long and thin and then does some weird stuff. This one is on a more elliptical orbit, so at some points it makes a shell and other points it has a long tail.
That one looks like Power 5.
Yeah. So these actually do look a lot like known globular cluster streams. This is sort of a profile of one of them in terms of the number of stars. So this is star by star simulation. We in order to model a globular cluster, you not only need to model the mass segregation, which means you need a star by star model. You also have to deal with the effect of the IMF and the aging of the stellar population. So these models also have compact objects, binaries, like all this stuff, right? We get it for free because Carl programmed it into his globular cluster model. And we can actually trace, I think this one and or maybe the other one has a binary black hole in it, like Gaia, BH3 that we're following up now. But anyway, the velocity dispersions in these things are as cold as we see in real streams, a few kilometers per second. And remember, there's no substructure in this model below L equals 8. And yet, you find substructure in the stream. So we think that this is actually a result of an interaction that a satellite had with a disk in this model that's been propagated back through the torques of the disk onto this stream, because the satellite itself is not in the model at all. We're trying to make sure that we have a good smoking gun for that, but we think that's what's going on here. So even without substructure in the dark matter halo, you can get substructure in streams, right? Another thing that people often do is look at the alignment between the tails of the stream and the track of its motion, which is these arrows, in order to constrain the overall shape of the halo. What we found is that this is dependent on the orbital phase, which is all these little insets. So this is like how far the thing is from the center of the galaxy over time. And so everything looks nice when it's close to pericenter, but then as it gets toward apicenter, the older stuff and the more recently stripped stuff and the older stuff no longer line up. So this is another place where you have to be a little more careful about what you're using to test your dark matter models. Oops, sorry. And then finally, another thing that people often do is they say, okay, well, I have this nice long tail, so the globular cluster that made the thing must be right here. But in this case, it's over here. And you're only seeing a part of the stream as being long and thin. And so the thing that we all took away from this is that what you can detect is going to be a lot different than the complete structure of the stream. And the next step is to turn this into some systematic predictions over an entire population of globular cluster streams in the same simulation. So this is a teaser with a handful that we already integrated. And there's a lot going on here, obviously. Some of them look nice and thin, others of them are really kind of weird. And this is all, again, in a model that has been smoothed over all the small scales. Yes.
I realize that I'm about to say something off topic, so feel free to not answer it, but I get this, and this makes very good sense to me. And when we were studying PAL 5, we started to realize that stuff is way more complicated than we thought it was, but we never really understood why the simple picture of stream generation is wrong. You know, like
that's what we're trying
turns out
to
it's
do
very
with
sensitive.
this.
Like,
Yeah.
turns out the stream, this beautiful picture that the stream should just grow
Yeah.
in and equally in both directions is obviously correct, and yet somehow it's very fragile in the sense that if you make any change to the because we just put in a bar and it suddenly
Yeah,
broke,
and it's like boom.
you know,
But then
and
that's not
here
the
you
stream
put
you
in just
saw.
a little bit of wiggly
So
stuff.
so yeah,
Little
just a
bit
little
of
bit of wiggles and you start to get some weird stuff.
So do you have a
But the
sense
real
of
missing
why?
ingredient here that I think we're ignoring is the detection bias.
Well, right, that's true too. These won't look like
Right?
this in detection.
You won't even see most of
No,
this
no,
stuff.
right.
You won't say,
Right.
oh, there's a stream.
Yeah.
So the next thing we want to do now that we have this statistical sample is like, okay, which of these things, if we were going and looking for them, would we actually see as a thin stream? Because I don't think it's everything. And until you take that view, I don't think there's any way you can know. It may be that there's a whole bunch of other crap out there. This is not even close to the full sample of globular clusters from this
Great. So your
simulation.
answer to my question is you're not even asking the right question.
Yeah, kind of.
But to that point, there was something you went fast
Right.
and I didn't understand. I know a couple slides back you said along the stream, you know, the
Oops, that's the wrong way.
this
Oh yeah.
so so I guess the red and the yellow, so that stuff gets tidally perturbed along a different axis
Yeah.
than the older stuff.
Yeah.
So that's just the tidal field is changing.
Yeah, and so this is another underappreciated thing is that the shape of the halo, because there's got a disk sitting in the middle, and then it knows about different stuff at larger distances. As you get farther and closer away, the principal axes are different, so the tides work along a different direction. Plus, even in a like moderately axisymmetric potential, you're gonna see a different amount of that effect at different places along the orbit. Right, just
And that can lead to clumping. I mean, it seems like it could lead
it,
to
and
clumping.
so the stream will always clump up a little bit at epicenter, but this thing is long enough that not all of it is at epicenter at the same time. There's a lot going on here, I know. This slide is really for people studying like the ears of globular clusters. But there's a lot of cautionary tales in here, and I think one of the big things is what I was going to talk about next, which is getting a detectability filter over all of these predictions. All right, so let me sum up about this so far. So I think we should set more realistic baselines for what kind of structure we do expect in streams before we go off and interpret everything that we see as dark matter substructure. But we can capture the kind of disequilibrium and the dynamic range very easily by using different models for the Milky Way. The extent to which you can fit these to actual data is not a question that I'm dealing with now, but I also think it's not crazy to simplify the models that we're using to represent these cosmological galaxies down to the point where you don't have that many more parameters to fit than a parameterized model would. Even if you start to include some time dependence. And I think the time dependence that's most important to include, we also have some more insight into that now. And it's generally speaking, just changes in the shape of the halo over time that I think are the real important part to get right.
What do you mean about force reproduction solves dynamic range problems?
Right. So what I mean by force reproduction is using the basis function expansions to apply forces to things rather than having to do a full n-body simulation. And if you were to try to put the stars from one of these model globular clusters into a cosmological simulation and run the whole thing forward with n-body, you would run into a lot of problems because there's a mismatch between the masses of the particles in the simulation and the masses of the stars in the globular cluster. So you'd end up with a lot of unphysical noise. And so this bridges that gap in dynamic range to let you simulate those two things simultaneously, the large scale evolution of the galaxy and the small scale dynamics in the globular cluster.
One thing I don't understand, but maybe it's too dumb a question to answer except later, but the fact that you make this analytic, so I understand the analytic parts that remain kind of familiar polynomials, but when you make the spline and it's not radially symmetric, I don't see how how do you, it seems like you still have to do everything numerically. Are you just saying that the numerical part is simpler because it's less structured?
It's far simpler than doing a full n-body simulation.
Yeah, that's certainly true, I guess.
That's all I'm saying.
Okay, so but just to be sure I understand, at each time step, you respline, you refit to get new splines?
So at each snapshot that we save the galaxy's configuration, we refit the whole thing. There are instances in which we don't do this thing with the splines, and because if you want to study like how the power at different modes in the basis functions couples over time, then you don't do it with splines. You decide on a basis for the radial functions, and you fit the same basis to everything. And then you can do time series analysis on the coefficients and get a lot of information out of it. I didn't have time to put that in this talk, but we can talk about it later if you want.
Okay, wonderful. That's so great you're doing this. Okay, I'll shut up.
But it truly is, but to emphasize, it truly is analytic in the mathematical sense,
Yeah.
not in the sense that you can write it down on a piece of paper, not that sense of analytic, but analytic in the sense that
It has
you
well-defined
have
derivatives.
well-defined derivatives
Yeah,
in
everywhere.
all directions except possibly time.
Yeah.
I was gonna ask about
Yes.
that actually. How about the time? Are you also having smooth functions in time?
So all we do is linearly interpolate the forces between the two nearest snapshots. It's
You
important.
could learn a differential equation in principle. You could learn the differential equation that connects them.
Yeah, we're
in
doing the
time.
dumbest thing because it worked well enough.
Because if you wanted analyticity, you could even get that in
Yeah.
time, I suspect.
Why not
Because you're
spline
so
in
clean.
time, just like you have said?
We actually tried that, and where it matters to do the spline in time is actually in centering the coordinate system that you use to model to like fit the BFE on the center of the galaxy. Because cosmological simulations, right? You zoom in on a box, there's not like the global momentum is not zero. So the galaxy just sort of wanders through the box. So you have to recenter it every snapshot. And doing that is actually kind of a pain. And the centers end up being pretty jerky, and you don't want large fictitious forces from recentering in every snapshot. So you fit the center and then you spline it. And so that worked really well. But this is we haven't gone beyond just like linear force interpolation because it seems to work fine for the stuff that we're doing. I think the key there is that we're interpolating the forces and not the coefficients of the model too, because that keeps you in the physical world, right? The potential is a figment of our mathematical imagination. And if you interpolate the coefficients, then you get into problems with like negative mass and things, and then it gets weird. But if you just calculate the forces and then interpolate them, then you're fine, because that's like the thing that the orbits actually care about. All right, so we can do much more reliable modeling of things if we just relax some of the assumptions that we've been using all this time. And I think we have enough data now to do it. But more importantly, I think for the dark matter aspect, we can start now to figure out which going back to your question, which dynamical processes are the ones we really need to get right in order to get believable and robust and like meaningful constraints on dark matter models from this kind of analysis. All right. So we also can make new discoveries. We saw that the LMC is going to change the local density of stuff. So on one hand, you don't want to misinterpret your result into the wrong density of clumps. But on the other hand, you could be like, okay, well, the LMC is going to make more clumps over here. So I'll go look at those streams so we can maximize our probability of a detection. I think it's very promising that our best effort at self-consistent simulation is producing stuff that looks like the streams we actually observe. I don't know yet, because we haven't done the full statistical sample, whether the numbers are going to match up. But it's promising. But that comes with the caveat that the coldest streams can even be clumpy without dark matter subhalos, just from their interaction with the evolving disequilibrium in the galaxy. And since they're cold, that's not so surprising, right? The reason we're using them to detect dark matter clumps is because they're sensitive to tiny changes. So we just have to make sure that tiny changes we can actually tell them are coming from dark matter and not something else. All right. So now going back to this detectability thing, which I think is the missing link for this problem and for many others, I would call this just making principal comparisons between our predictions and observations. So I've worked a long time in this. Basically, scientific history is littered with instances where there was a discrepancy between the predictions and the models that went away when somebody did a better job with the selection function, right? So the missing satellites problem is one of these, right? So way back in the day, there were predictions from CDM about how many subhalos you should get as a function of mass. And then somebody went out and counted and like, oh my God, there's a factor of 10 difference between how many we see in satellite galaxies and how many we count in our simulations. But of course, if you do both better modeling and better correction for the selection functions, this goes away, right? So the correction for the selection function here is between this bottom line, which is the actual counts of satellites, and the upper black line, which is resampled for or weighted for the selection function of the dark energy survey, which is and combined with pan stars, which is the data that these were from. And then the shaded stuff is predictions from simulations. So just fixing this, the detectability question, turn this from a problem into a solution.
MV is what?
Oh yeah, this is a proxy for mass. It's the total visual magnitude of the satellite. So like less negative
mass.
is, yeah, so this is like a stellar mass. And you can put the simulations on better footing by doing some additional work to map their like stellar mass component to a stellar luminosity to get that number. That also has a little bit to do with this, but it's mostly just like which ones you can detect and which ones you can't. All right. So we actually went back and did the same thing with streams, which is how I know. So streams would be an independent constraint on this same thing. Because they're just disrupted satellites, so they should, our prediction should jive the same way, right? So in the dark energy survey, Nora found 2 streams that are within the resolution limits of our simulations. And if we go down to the same limit, we predict 8. All right. So that sounds like a problem. But if you actually correct for the ones that you could detect, then the whole thing goes away and the streams are all right too. Okay, so this is just a little case study of like why this is so important and why I think it's going to be equally important to understand what we can get out of globular cluster streams. Because the other thing we found, for example, here was that a whole bunch of things that we called streams, when we have perfect knowledge, you detect just the progenitor and think that it's a satellite galaxy. And this prediction is now coming true. People are finding the beginnings of tidal features around a whole bunch of satellite galaxies that we thought were just intact. But if you account for the observational bias, then you resolve the discrepancy, just as was the case for the intact satellites of the Milky Way. All right, so under the hood, what you actually have to do is turn the particles that represent stars in your simulation into individual stars. You have to choose a model for your stellar populations. You have to estimate what the density is everywhere so you can spread out your stars into the phase space that they would occupy locally. Oh, sorry. And so that'll give you what I would call mock catalogs. So you've now got a fake star that is representing each particle. And then you describe how your survey sees things, right? What is its color limits, its magnitude limits, what extinction do you put on it, and whatever. And then you get a fake survey of your simulated galaxy. So this is an example where we did all this for Gaia. And you can get a really nice correspondence between the real and the fake. I will not insult you by asking which one of these is real. But it's pretty convincing, right? So we've been doing this for a while now, and in fact, lately the big news is that we have a public code that's professionally maintained by this guy who's a research scientist at Penn with me. And you can now just pip install this and apply it to your own simulation if you want to. And we're working on some recipe books for it. But if you're interested, please let me know. So the reason that we've started to think about globular cluster streams, as I said before, is because of the Robyn Space Telescope, which is launching at the end of next year. September 2026, guys. Oh my God. And the reason this is going to be so cool is sort of twofold. One is that it's like Hubble times 100. So this is a picture of the Andromeda Galaxy, which is our closest big neighbor. And this blue outline is the FAT survey, which was like hundreds and hundreds and hundreds of orbits with Hubble that surveyed this big chunk of M31 in resolved stars. This white thing is one Roman pointing. So this is going to be a machine.
That's a sick.
Isn't it sick? Come on.
Yeah, I agree. I was rolling my eyes when you said it's much better than HST, but now maybe I agree.
So it's 100 times the field of view with the same resolution and a more sensitive detector in the infrared.
And how does it compare to the JWST?
So JWST, the field of view is tiny,
Even
right?
smaller
This is one
spaces.
Hubble footprint, that's comparable to JWST. So for when you study resolved stars in nearby galaxies, what you will do in the next generation is use Roman to get all the outskirts, and then JWST for the inner part, where Roman doesn't have the resolution to distinguish, because JWST is a bigger telescope, so you can distinguish individual stars to much closer distances.
By the way,
Anyway,
JWST's lifetime is limited, so they should anticipate
uh,
what
we,
Roman can't do.
I was just
Are you
on a
putting that in?
proposal that
Good.
went in at this call for
That's a good idea.
JWST to literally do that.
Right, to anticipate what
Yeah.
Roman's gonna ask.
How long can Roman last?
So Roman also nominally is 5 years, but could go longer if there's funding. Eventually, it will also run out because it's going to be at L2, so there's some like consumables that will limit the life of that mission as well.
And how much longer does JWST have?
I don't know.
It's not known, but it could go for a full 20 years, I think, it is the current hope. Which would be 15 to go.
Still very long.
It's great. The other thing that I'm not going to talk about here, but which is in the other awesome thing about Roman besides this situation with the field of view and the exquisite resolution, it's also like the best astrometry telescope that we're going to get forever. And part of that is because anything that Hubble saw 20 years ago, you can cross match to anything that Roman's going to observe and get these stupid baselines for proper motions. Even just within the 5-year baseline for the Roman core surveys, one of which is going to look at a bunch of the halo, you get like proper motions that correspond to interesting velocities in the Milky Way's halo. Ask me about that. I wrote a whole paper on it. And we're reviving this stuff now because we actually have like mission plans and stuff. But one of the things we can do is figure out how unique the Milky Way is, since now we can see other galaxies in resolved stars. And so we're looking at doing this both within the galaxy for the Galactic plane survey. For nearby galaxies, these are all fake images, by the way. All synthetic surveys. This is a thing that looks like Sene. That just we found a snapshot that looked like that. And here's the stellar halo of another simulation in star counts, as you would see it at I think 7 megaparsecs with Roman. This white square is a degree. And then we're also going to propagate our globular cluster models all the way through to see how far away we could see hints of stuff with Roman. And so I think this is really what you have to do in order to know what you're going to expect, in order to look for, signals of new physics. All right. So the other thing we're doing, speaking of which, is to make these kind of predictions for some more dark matter models. So cold dark matter, things with self interactions, things where the dark matter has like dark hydrogen. And so you get much more concentrated central densities. And these little clumps that bounce around in the halo. My postdoc, Stephanie O'Neill, is working on this with a grad student at Princeton, Lucas Guerra. And so I think both of these things will let us actually put believable constraints on dark matter. Gaia basically showed us where our theories were failing us, among many other interesting discoveries. But from a dynamical standpoint, and especially in recovering the distribution of Milky Way dark matter, it spurred some theoretical improvements. And to use those improvements to make these kinds of falsifiable tests with mock data is really what I think is going to harness the power of these new observations for constraints on both dark matter and galaxy formation. Thanks. Wow, I was actually on time. Cool. Questions?
Liz, more questions? So
I mean, I've always had more questions, but in the end, you did successfully avoid my question, my hard question, which is why are these the default idea about streams is that there's some tidal tensor, things fall out and then they trail or lead the satellite.
Yeah.
That more or less illuminates an orbit of the satellite. It should do so more or less symmetrically. Why is that picture fragile? Like, I know it's fragile because we've also done simulations like this and find that it looks like shit.
Yeah.
But even though the analytic position is undeniably true, any numerical simulation looks bad. Give me a explanation
So I know
that I
that
can tell
ours
my children.
are fragile. And it's because the things that make Liouville's theorem work for streams all are predicated on a symmetric and like a certain level of symmetry in the potential and a certain and time independence. And so the Milky Way breaks both of those assumptions. And it's not like the equations of motion aren't perfectly separable. So you have a little bit of more like ways to leak out there. And you don't have, and the number of degrees of freedom is like, you know, not quite 2. You know, it's like a little more than 2.
Somehow it is,
Right? So that's one thing.
Yeah.
And then the other thing is that like stuff happens. And so like d phi dt isn't 0, and so you can't quite use Liouville's theorem the same way.
I mean, Liouville's theorem is still in play. It's just that it's in play in some horrifying coordinate system.
Yeah, it's like you have to really think about more. So like the mental model of a stream is like a line in 60 phase space is almost right.
Mhm.
The other thing though I will say is that classically people have thought about streams as a line not in full 60, but in like a subspace. Right? And so like a lot of people's mental models of streams are on circular orbits, so you can ignore the radial coordinate and VR. And so that reduces your subspace, and that reduces the degrees of freedom that your orbits have to leak away from or that the stars have in the stream to leak away from their parent orbit. Right? But really what you get, and especially since cosmologically, everything is on a radial orbit, right? Because accretion. So the times that you get a circular orbit that's not the default. And so you have to then take your mental model of your one-dimensional line in 6-dimensional phase space and like rotate it to some weird angle in all 6 dimensions. It's still a stream. It just doesn't look like one when you project it down onto what we call observable coordinates.
Okay, so does that mean that in principle we could imagine we could find tons and tons of streams? Some people would say we already have, but I really mean the horrifying parts of your streams that don't look streamy. Imagine we could find all that. Would we then be able to learn like a horrifying diffeomorphism that if you applied it, everything would come back out to be lines?
Yeah, that would be the actions. And the angles.
So maybe that's a good idea.
So we've tried that with these systems. Not with the globular, not with not with the globular clusters, but with the streams in the satellite streams.
Yeah.
And for some of them you can get beautiful transformations to action space. And for others it's like impossible. And the times when it's impossible is when you have like an LMC mass or larger thing that comes in and bothers your potential so that the separability goes away.
Yes, and you won't have actions at all, or that you won't have trivial.
Yeah, so the weird thing is that what gets messed up is always the phases and not the clustering and the constants of motion. So
right. So the basic constants of motion are still useful. It's just that you don't get the beautiful phase separation.
Yeah, so you don't get like you compute angles and they just get all weird.
Good, great.
But the clustering in phase space or the clustering in the action still works, but the location of the cluster is no longer corresponds to where it was initially.
Right, okay.
So stuff is still correlated because otherwise you wouldn't have a stream. But Otherwise, but it's like the clump of actions is located somewhere else in phase space than it was before the merger, before you got time dependence in your potential.
Good.
Right, and so for certain kinds of time dependence, you can accommodate that in your definition of your actions, right? You can use the Jacobi energy or whatever. But for something that is also breaking the separability of the equations of motion, then you can't, which is what mergers do. Right, because all of a sudden you have an extra symmetry axis that's the line joining the two things. And so yeah, that's where that breaks down. You can get away with it though, pretty far up the mass scale. You can almost get away with it,
I
even
see.
depending on what you want to do. And so like the thing that we developed, which minimizes the clustering in action space, still works if you have an LMC. You just can't then take those actions and say that the thing is a stream on this orbit. And
I
so
see,
that's
yeah.
where the progenitor came in, because it's relocated.
I see, yeah, good, great.
So it may not be phase mix, but it's lost some of its memory of where it came from.
Good.
We looked at that specifically because everybody was freaking out about the LMC and how it messes up everyone's orbit models. But yeah, I think it's a combination of things. But I really think that until we know which of those things we would actually call a stream, we don't know the answer to that question.
Fine.
Because like you get all this diffuse structure,
Yeah,
and it's almost like an anthropic principle for streams, right? Like
Yeah.
if we wouldn't call it a stream, is it really a stream?
Right, and it looks like a lot of the interesting information is actually in the diffuse structures. When I look at your thing,
Yeah.
it looks like it's those roses that are the end of the stems.
Yeah, it's
That
the messed
contain
up
a ton of
stuff.
the information. We know that's true for PAL 5. We know that the mess that happens at the end of PAL 5 is very informative about the bar.
Yeah, but the surface brightness effectively
But then
that
it
you need to
immediately
get to.
disappears. You lose it as soon as it
Yeah.
becomes a mess. You lose it.
Like it's really hard. It's easy to tell that the long thin part is all part of a stream.
Yeah,
It's
and then-
really
but
hard
it's
to
that
pick
thing at
out
the end.
stars that are doing like
Right. A lot of these have like a rose at the end of
Yeah.
the stem. And I'm sure
Yeah.
that's everything interesting.
You're very poetic. David.
Well, we have to, I mean, the poetry
With the
works in
roses.
this field. We're astronomers, we work on poetry.
Sometimes we call it sausages.
No, no.
That was not a good thing.
Lagerholm is the anti-poet.
That is accurate.
We're on the other side of that. Catherine would love that explanation that you guys gave, by the way.
So in your like one of your last slides, you showed like atomic dark matter. This
Oh yeah.
So is the plan to redo this spherical harmonic decomposition, etc., and then do the whole for
Yep.
like to do simulations first, and then so of course grain the simulations.
Yeah.
Does-
So
does-
we already have a lot of the simulations and we're gonna look. So there's another layer to this with the dark matter that I think is really interesting, but I didn't have time to talk about, that you can do with the same basis function expansions. And because what's happening under the hood with your global evolution of your galaxy is that you have like a disk forming in the middle and you have your halo, and then everything is sort of building up from these filaments that are controlling the large scale structure around the galaxy. And if you fit these time series of basis function expansions, you can, in the way that I described to Glennis, where you fix the basis and then you do the time series so you can interpret the coefficients as a time series. Then you can separate out scales in both space and time just using strategies of time series analysis. And so you can ask, like, what parts of the formation of a galactic halo come from the external imprint of the filaments, and what parts come from mergers, and what parts come from coupling between the disk and the halo and all this other stuff. Because those all happen on different dynamical time scales and on different physical scales. And so you can use the same approach to do that. And that's one of the things that I really think is going to be key once you start going away from like cold dark matter, because cold dark matter has like the weakest possible coupling between standard model and everything else, right? It's only gravity. But the response changes once you introduce a self interaction, right? Or once you let some of the dark matter be like something that can cool, right? You change the gravitational response because you change the ability of the dark matter to redistribute as the disk of the galaxy grows and all this stuff. So that's one thing that I want to do with these, apart from just redoing all the like globular cluster things that we did. And the like, we have a paper coming out actually that is looking at what the streams look like in these atomic dark matter simulations. So it's and there are distinct differences that come from the fact that the density is different both in the main galaxy and in the small galaxies. And so there are testable predictions even there that you could make just by like fiddling with the dark matter model and pulling through some of this stuff. And that's before you even get to the mock observations, which we can also do. So the key to all of this stuff is that we deliberately selected a baryonic model that at least works for CDM to make believable galaxies that's been well tested. And the same exact initial conditions as far as physically reasonable for every single dark matter model. So it's the closest to a true apples to apples comparison that we could get to. At a level of detail that I think will be illuminating. So that's not something that is going to lead to a big parameter space exploration, right? Because these are costly, but it'll at least point us towards what are the right figures of merit for these observations if we want to distinguish between these things. Because I think we still are a long way from knowing that.
Are you also gonna make Gaia mocks out of all of these?
Sure.
Because in principle, there might be Gaia observables.
Yeah.
that are
So
different.
actually, what our plan is to publish the kernel so other people can make their own Gaia mocks.
Mhm.
Because the code is public now.
Good,
You can
that's
do that.
great. That's good.
And I don't have time to do it.
Yeah,
but
yeah, and
other
it's a
people do.
non-trivial matter.
Yeah, I let alone time, I don't have disk space to do it.
Yeah, right, yeah.
But if somebody like basically what we're leaning toward with Roman is making Pyanonke available on the Roman Science platform with a bunch of example data so you can make your own mock Roman observations of our simulations and then compare them right on the platform to your data. That's where we're trying to so that when somebody comes up with a variation or they want to use a different simulation to compare to or whatever, they don't have to come and talk to us. They can just do it. Because there's more and more of that people are going to want to do, even beyond what we did with Gaia.
Sure.
And even the Gaia stuff I would do differently now, because there were questions that people wanted to answer with it that they couldn't answer with the way that the decisions we made in our mock survey. And that's just a function of trying to be all things to all people.
Absolutely. Okay, we should thank Robyn again.
Thank you guys.